9.10 Lesson 1, Taylor and Maclaurin series. Our objective for today's lesson is you'll be able to use the definition of Taylor series to find Taylor series for functions at specified centers, vocabulary, Taylor series, and Maclaurin series. Before we do that, I'd like to spend a couple of minutes to relate what we want to accomplish in 9.10 to what we did in 9.9. In section 9.9, we looked at representation of functions by power series. So the main idea from section 9.9 is if you have a function that can be manipulated to look like a over 1 minus r, which is, of course, the sum of a convergent geometric series, when the absolute value of the common ratio is less than 1. So the main point of section 9.9 is if you have a function that can be algebraically manipulated to fit the form a over 1 minus r, you may represent that function with a geometric power series, and you would know the interval of convergence for it. And there were other functions that we could not write in the form a over 1 minus r. However, we were still able to find power series representations for those functions, such as, for example, f of x is equal to natural log of x, because we noted that natural log of x is the integral of 1 over x dx. And we were able to find a geometric power series for 1 over x centered at, for example, c is equal to 1, and then integrate that geometric power series to find a power series centered at the same value, for example, c is equal to 1 for natural log of x. In the same way, we were able to do the following problem using similar reasoning. Although the function arctangent of x cannot be written in this form, we recognize that the derivative with respect to x of arctangent of x is 1 over 1 plus x squared, which can be algebraically manipulated to fit this form. So we were able to write a geometric power series for the derivative of g. So we could integrate our geometric power series to find a power series for the arctangent function. So everything in section 9.9 went back to this theorem from the early part of chapter 9 about the convergence of a geometric series. So we were able to represent functions that could either be algebraically manipulated to fit the form a over 1 minus r, or functions whose derivatives or whose integrals could be algebraically manipulated to fit the form a over 1 minus r. That allowed us to represent a wide range of functions by power series. However, it was limited in that your function, you either needed to write it in the form a over 1 minus r, or possibly its derivative or its integral in the form a over 1 minus r. There are some functions for which that cannot be done. So the approach that we took in 9.9 will not work for functions that cannot be written in the form a over 1 minus r, or that has derivatives or integrals that can be written in that form. Such functions include f of x is equal to sine x. We can't find a power series representation for sine x relying on the method from 9.9, because sine x does not look anything like a over 1 minus r, and its derivative is cosine, which does not look anything like a over 1 minus r, and its integral also does not look anything like a over 1 minus r. So there are some functions, such as the three that I'm mentioning right now, for which we need to find power series representations using a different approach than what we did in 9.9. So that's what 9.10 is about. And we'll be looking at that in the lessons that follow today's lesson. Today's lesson won't get into that, but it's going to lead to lesson 2, lesson 3, and so on. But at the beginning of 9.10, I wanted to tell you what the section is all about and how it relates to 9.9. So now we go back to our objective for today's lesson. Today's lesson is one in a series of lessons for 9.10, and our objective is you'll be able to use the definition of Taylor series to find Taylor series for functions at specified centers. So we look at the definitions of Taylor and Maclaurin series, and for reference, I want you to remember what we did in section 9.7. In section 9.7, we studied Taylor polynomials and Maclaurin polynomials, and in section 9.10, we're looking at Taylor and Maclaurin series. So basically, the relationship between the two is, with the Taylor polynomial, it stopped at a particular degree, but with the Taylor series, it keeps going forever. But you form the coefficients in the same way, and you can see that by comparing the definitions of the two. So in section 9.10, we have definitions of Taylor and Maclaurin series. In section 9.7, we had definitions of nth Taylor polynomial and nth Maclaurin polynomial. 9.10, if a function f has derivatives of all orders at x is equal to c, then the series, and this is an infinite series, and this is the general description of the nth term. You have x minus c to the n power, and the coefficient is the nth derivative of f evaluated at c divided by n factorial. And if we just write out the first few terms of it and the nth term, that's what it would look like this. The series would look like what you have here. The terms of the series would look like that. This is called a Taylor series for the function f of x centered at c. If c is equal to 0, then the series is called the Maclaurin series for f. Compare that to what we did in section 9.7, where we learned about nth degree Taylor polynomials and nth degree Maclaurin polynomials for functions centered at c. If c is 0, we had an nth degree Maclaurin polynomial. And take a look at what we had in 9.7 and compare it to what we have now in 9.10. And you'll see that it's the same. F of c, f prime of c times x minus c, f prime of c times x minus c. The nth derivative of f evaluated at c over n factorial times x minus c to the n. The nth derivative of f evaluated at c over n factorial times x minus c to the n. And as I said before, the difference is in section 9.7, this is where it stopped. It was an nth degree Taylor polynomial approximation for the function f centered at c, but in section 9.10, it keeps going forever. And one of the things that we want to consider in 9.10 is, if in 9.7 an nth degree Taylor polynomial approximated the function f centered at c, and we observe that the higher the degree, the better the approximation. So the question then becomes, well, what if we have an infinite Taylor series? How would that relate to the original function? Would it be an exact representation of the original function from which we derive this Taylor series? That's basically the question that we want to ask in this section, and we'll be looking at that question tomorrow. We know that in 9.7, an nth degree Taylor polynomial approximated the function centered at c, and the higher the degree, the better the approximation. So our question in this section is, in 9.10 is, if we have a Taylor series, will it represent the function from which the series was derived exactly on its interval of convergence. And we'll be looking at that tomorrow. But for today, you want to understand that a Taylor series is like a Taylor polynomial, but unlike a Taylor polynomial, it has infinitely many terms. A Taylor polynomial has a finite number of terms. So that's a Taylor series, and that's how it relates to what we did in section 9.7 with Taylor polynomials. A Taylor series, like a Taylor polynomial, is centered at C. A Maclaurin series, like a Maclaurin polynomial, is centered at 0. If C is equal to 0, the series is a Maclaurin series. So here we look at example 1. It states, use the function f of x is equal to sine x to form the Maclaurin series. So we know the center is 0. And again, we're just looking at the definition of Taylor and Maclaurin series with the center C being at 0. So this is what we need to have. And that's exactly what's given here. F of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared, and it just keeps going forever. So we want to form the Maclaurin series for the function sine x using this definition of a Maclaurin series, which obviously relates back to what we did in 9.7 with Maclaurin polynomials, and determine the interval of convergence. So we need to find the values of these coefficients in our series. So we begin by finding derivatives of our function and evaluate the function and its derivatives at 0. And we want to see if perhaps we can detect some kind of a pattern. So we have our function is f of x is equal to sine x. The first derivative of it is cosine. The second derivative of our function is negative sine. The third derivative of our function is negative cosine. The fourth derivative of our function is sine. And you can see that you'll have a cycle here, because now we're back to what we had originally, so our cycle will just repeat. The fifth derivative of our function will be cosine, and it just keeps repeating. So if you evaluate our function and each of its derivatives at 0, this is what we'll have. Sine of 0 is 0, cosine of 0 is 1, sine of 0 is 0, cosine of 0 is 1, so you have negative 1, sine of 0 is 0, and cosine of 0 is 1. And of course, again, the pattern repeats, so you have 0, 1, 0, negative 1, and that will just repeat, because the fourth derivative is the same as the original function. So that pattern of 0, 1, 0, negative 1 will continue to repeat. So we make that observation, and we're able to do the following. So here I'm just rewriting the definition of a power series with center at C is equal to 0. So we have x minus 0. And it would be easy for me to write additional terms because I know of the repeating pattern of the 0, 1, 0, negative 1. I can use that to write additional terms if I'd like to. what I'd like to do now is to determine the interval of convergence for this power series that we derived from the function f of x is equal to sine x. So to do that, it's helpful to have a rule for the nth term of our power series. So let's see if we can come up with a rule for the nth term of this power series. So if we eliminate the zero terms and just write the non-zero terms, we'll have this. So we have x, and then we have negative 1 over 3 factorial x to the third, and then we have positive 1 over 5 factorial x to the fifth, and then we'll have minus 1 over 7 factorial x to the seventh. And what we're trying to do is we're trying to write a description of the nth term so that we may represent our infinite power series using summation notation in which we can write what the nth term is. So one thing that you will observe is this. This is an alternating series because the first term is positive, the second term is negative, the third term is positive, the fourth term is negative, and so on. So we can have negative 1 either to the nth power or the n plus 1 power. If I start my index at 0, then yes, I would like it to be to the nth power because negative 1 to the 0 is positive 1, and of course I want my first term to be positive because it should be positive x. And if I choose to start my index at 0, then I need to figure out what x should be raised to and what my denominator should be. One thing that you will observe is that as I go from term to term, you will observe that the power that x is raised to is an odd integer. It's an odd integer. And you will also observe that in the denominator you have that same odd integer factorial. 1 factorial here, 3 factorial, 5 factorial, and 7 factorial. So whatever you write here, you'll have the same expression and factorial in the denominator. And because they're all odd, we're going to try 2n plus 1. If n is 0, I get 1. If n is 1, I get 3. If n is 2, I get 5. If n is 3, I get 7. So this works. So we have 2n plus 1 factorial. So this is what you write for the nth term. And then we're going to find the interval of convergence by using the ratio test. So now we'll go ahead and use the ratio test to determine the interval of convergence for this power series. And this power series was derived from the function f of x is equal to sine x. So to determine whether to determine the interval of convergence for this power series derived from the function f of x is equal to sine x, we use the ratio test. What is the interval of convergence for this power series? So we take the limit as n approaches infinity of the absolute value of the quotient of the n plus 1th and the nth terms. So how do you divide? You multiply by the reciprocal. So that's what we're showing here. And you can get rid of the negative 1 to the n plus 1 power and the negative 1 to the n power because we have absolute value, and those two parts are just giving you either a positive 1 or a negative 1. And we simplify here. 2 to the n plus 1 would be 2 to the n plus 2 plus 1, which is 2 to the n plus 3. And we have the 2 to the n plus... I meant to say 2n plus 3, not 2 to the n plus 3. So we have x to the 2n plus 3, and in the denominator we have 2n plus 3 factorial, and we're multiplying that by 2n plus 1 factorial over x to the 2n plus 1. So, of course, you can use properties of exponents. So x to the 2n plus 3 can be written as x to the 2n plus 1 times x squared. You have a product of powers with the same base, so when you add the exponents, you get 2n plus 3. 2n plus 3 factorial can be written as 2n plus 1 factorial times the other two integers that come after 2n plus 1, which would be 2n plus 2 and 2n plus 3. And when you do that, you can see that you can cancel common factors. X to the 2n plus 1 can be canceled. 2n plus 1 factorial can be canceled. And here's what we are left with. Because n is going to infinity, I don't really need absolute value for this particular quantity here. And I have the absolute value of x squared. And we're taking the limit as n is going to infinity, and x is independent of n. X could be any number, but it's independent of n, so we consider x to be some fixed constant. So you can factor that out of the limit. You don't need absolute value for x squared because x squared is going to be non-negative. So you have this. And of course, if you look at the limit that we have now, the numerator is a constant, and the denominator, as n goes to infinity, will go to infinity. So that limit is equal to 0, which means that regardless of what x is, the limit that we began with for the ratio test will always be 0 for any x, which is less than 1, and by the ratio test, therefore, the power series will converge for any value of x, because the limit for the ratio test is less than 1, which means by the ratio test, the power series will converge absolutely for any value of x. So here we have number 7. Use the definition to find the Taylor series centered at C for the function. Our function is f of x is equal to sine of 2x, and the center is C is equal to 0. So just like we did in example 1, and just like we do for any problem of this type, we need to find what the coefficients are in our power series. So we need to find the derivatives of this function and evaluate the function and its first few derivatives at C is equal to 0. And then we'll be able to write the power series, the Taylor series, for f centered at 0. So we find the first few derivatives of our function. We have to use the chain rule because we have a composition of two functions. And then we evaluate the function and its first few derivatives at 0. And we get 0, 2, 0, negative 8, 0, and so on. So using that, we may go ahead and write our Taylor series for the function centered at 0, or a Maclaurin series. I will stop here and leave it for you to continue with this example. What you can do is you can find maybe the 5th derivative, the 6th derivative, the 7th derivative, and the 8th derivative of the function f, and evaluate each of those derivatives at 0 so that you can figure out parts of the coefficients in your Taylor series. And maybe you can get a couple of more terms that you will have after negative 8 over 3 factorial x cubed. And once you see that, once you have that, you may be able to see a pattern, and you can relate this back to example 1. The only difference between this problem and example 1 is in example 1 we had f of x is equal to sine x, and in this example we have f of x is equal to sine of 2x. You may be able to see some similarities between the two Maclaurin series for the example and for this particular problem, and see if you can notice some patterns about the coefficients and write a description of the nth term. So you can write the general nth term and represent the Taylor series centered at 0 using summation notation, and compare that to the summation notation for the Taylor series for f of x is equal to sine of x centered at 0. You may notice some pattern as you go from f of x is equal to sine x to f of x is equal to sine of 2x. And we'll be talking more about this in the lessons to follow. So today we begin our study of section 9.10. At the beginning we spent some time talking about the connection between 9.9 and 9.10 and what we're trying to achieve in 9.10. We were able to use the definition of Taylor series to find Taylor series for functions at specified centers, and we referred back to what we did in section 9.7 when we studied nth degree Taylor polynomials.